So I welcome you all to this seminar, all of you here in this room, and we have also audience on YouTube, a YouTube broadcast. And today we are going to witness or participate in the presentation of a thesis in electronics, and the presenter today is Muhammad Saad Shaikh. And the title of your work is Hyperspectral Imaging for In-situ Applications. Yeah. And the supervisors for this work has been me, myself, and also Professor Mattias O'Nils that we have here in the room. And we are very delighted to welcome the opponent for this presentation, Professor Jocelyn Chanussot. I hope I presented or pronounced it almost correctly. From the university in Grenoble.
Good morning.
Good morning. We have a grading committee of 3 gentlemen. We can start with our guest online, Paul Scheunders from the physical department at the university in Antwerp. Welcome. Good morning. And we have Jaime Zabalza from the university at Strahclyde in Glasgow with us here in the room. We welcome you. And from our own faculty at the Mid-Sweden University, we have Associate Professor Jonas Örtegren. And I think now we are almost ready for the start of your presentation, Saad.
Thank you.
But before you make the presentation, you still have a possibility, if you have a list of errata, some things that you want to correct, you can start with this kind of presentation.
Yeah, thank you for giving me this chance. Actually, I was able to spot these 2 things that I would like to mention. In the thesis, the heading 1.4.1, it has some issue. The word using appeared 2 times. That should not be this way. And in paper 1, the field of view for the used camera is mentioned as 18 degree, but that is incorrect. It should have been 38 degrees. Shall I start? No?
So, please go ahead with your presentation.
Okay. Thank you very much, Benny. Hello, everyone. My name is Muhammad Shaikh, and today I'm going to present my PhD thesis on hyperspectral imaging for in-situ applications. In next 40 minutes, I will take you to the introduction to my thesis. Then I will present the methodology, followed by the brief discussion on the results and the conclusions of the thesis. So let's start with the introduction. Spectral imaging is a technique in which the spectral information is presented as the 3rd dimension to a 2D image, a spatial image. And these stack of images are generally referred to as the spectral cube, as can be seen here. And spectral imaging can be categorized into 2 different fields, sometimes in 3, but generally in 2, multispectral imaging and the hyperspectral imaging, and it depends upon the number of spectral bands it uses and the spectral resolution. The area of application for spectral imaging also is divided into 2 categories generally. One is the remote sensing, in which the spectral sensors are put on board to satellite or the aircrafts. And the other set of applications are referred to as the in-situ applications, for example, hyperspectral imaging in food processing, manufacturing, military application, waste management, and etc. The motivation why we worked on this field of technology, one reason is its very vast area of application, as I already mentioned. So if we are able to make some improvement in some methods. They can be applicable to the different areas of technology and can have more impact. The other motivation for us to work on this field is its high potential in polymer recycling. The polymer waste is already a global crisis, and there has been a lot of efforts to deal with this problem. Hyperspectral imaging is already there and doing great job, but still there are some areas some issues that need more investigation and improvements. Here in this slide, the data from 2 regional companies are presented, where they say that with what type of polymers, what kind of purity of sorting they can have in their output. And we are motivated here to analyze any possible system limitation, environmental impacts, or other possible sources of error that possibly can degrade the robustness of measurements. The research problems that this thesis address: hyperspectral measurements and material classification can be influenced by various factors. In this thesis, we divide these factors into 3 subclasses. The environmental factors, like changes in light, temperature, and humidity at the imaging site. The system-based factors, like the limited dynamic range and the sensitivity of the camera, the limited operating wavelength of the cameras, non-uniform distribution of camera sensitivity, and the changes in spectral distribution of the illumination source. The third factor is based on the applications itself. Sometimes the applications themselves are tricky and problematic to deal with, and especially to classify. Research question. This thesis is aimed to answer these research questions. The research question 1, what are the major environmental factors that can reduce the performance of in-situ hyperspectral imaging systems? Research question 2, what are the major limitations of system components that can reduce the performance of in-situ hyperspectral imaging systems? Research question 3, how can we improve methods for image acquisition, processing, and system calibration such that the limitations and impacts found in research question 1 and 2 are mitigated? Research question 4, can the use of deep learning AI improve material classification by hyperspectral imaging? Research question 5, what have we learned from studying various applications for hyperspectral imaging? Thesis contributions. The first contribution this thesis claim is the calibration of hyperspectral imaging system using low-cost reference. In this regard, PTFE, polytetrafluoroethylene reference target, shown here, is presented as the calibration reference. It showed that it is insensitive to the environmental factors like humidity and the temperature, and the method that is proposed allows the material, dark current, and reference measurements at different exposure times. If we take a look at the related work, mostly another version of PTFE, that is the trade known by its trademark name Spectralon, is used. That is at least 20 times expensive than the PTFE, that PTFE version, another trademark known as Teflon. However, in some other works, the researchers presented the white paper sheet and also the cardboard as the calibration reference. However, these type of references are not insensitive to the environmental factors like change in humidity and the temperature. And this liberty of choosing the different exposure time for material, dark current, and reference measurement is completely missing in the related work. The second contribution is the HDR, high dynamic range imaging using hyperspectral line cameras. In this regard, a multi-exposure method for in-gas based hyperspectral line camera is proposed. The method is shown to result in to improve the dynamic range of the system and also to improve the classification of material. The related work is mostly deals with the 2D cameras that use CMOS and CCD photodetectors with the aim to increase the visual quality of the image, and we did not come across any study that proposed a multi-exposure algorithm for the kind of cameras we used in this research, and to investigate further the impact of this method on the classification of materials. Third contribution is the analysis of the impact of water vapor on shortwave infrared hyperspectral measurement. Contrary to the general belief or practice, the vaporized water, it is shown that the vaporized water has an impact on the measurements and also on the classification of material. Frequent calibration of the imaging system and pruning of the wavelength that are susceptible to the change of humidity are shown to improve the measurement accuracy and the classification of material. The related work we find in the area of remote sensing, where certain wavelength bands are considered blocked or unavailable due to the Earth atmosphere. However, it is taken as granted that in situ application, where the path length for light is comparatively very small, that the whole spectrum is available, but in best of my knowledge, no study was made to understand that if still there has some impact of water or the change of relative humidity, and what implications it can have on the classification of materials. The improved classification of multicolor polymers, it is shown that how the presence of color fillers affect the classification of polymers. Incorporation of visible wavelength with the short wavelengths in infrared region are shown to improve the classification for colored polymers. Different efforts had been made and presented in the relevant work. However, they reported difficulties in classifying particular plastic types with particular colors and different combinations of them. The fifth contribution is the performance evaluation of convolutional neural networks for classifying black polymers. In this regard, the effectiveness of CNN to classify black polymers using HSI within shortwave infrared is assessed. The CNN was shown to outperform the traditional machine learning algorithms. If we take a look at the related work, we will find that there is almost a general consensus that the black polymers cannot be classified using the shortwave infrared hyperspectral imaging. However, one particular study, this one here, the third one in this list, is shown 98% accuracy if the one-dimensional convolutional neural networks are used to classify. So basically, this was the reason we were pulled in to work on this issue. What we found as the result will be presented later at the end of the presentation. From here, we move to the methodology. In this work, we used basically one camera, mostly the FX17, and for some experiments, we used the FX10. Both are from the company Specim from Finland. The FX17 used in-gas sense photodetectors, while FX10 used CMOS 900 to 1700 nanometers, and 400 to 1000 nanometers are the spectral ranges of these cameras respectively. Both cameras use 224 spectral bands and prism, grating prism, PJP elements for the light dispersion on the detector. Both of them are the line cameras, line hyperspectral cameras. These cameras scan one single line on the surface, and against this line they generate a 2D output where each row is basically the reflection of the same line but in different wavelength bands. To have a complete scan of the area, it is necessary to either move the camera over the sample or somehow move the sample under the camera. The experiment setups. In this work, we mostly use two different experiment setups. One of them is mentioned here, where you can see a camera FX17 is placed between the illumination sources, all facing downwards towards the sample. This particular arrangement was chosen to avoid direct light going to the camera and to avoid the specular reflection as much as possible. Here comes the experiment number 2, where both cameras FX17 and FX10 were mounted on the aluminum frame on the top of on the aluminum frame, both facing downwards towards the polymer samples. The polymer samples were placed on a sheet that is covered by the foil paper, aluminum foil paper, and this sheet is attached to the stepper motor that allows us to move the samples for the scanning under the camera. This setup mimics the industrial setting where the conveyor belts normally have the products and there are sensors overhead to take measurements. The test applications and samples. In this work, we use different test applications to analyze the effectiveness of the proposed methods. One of such application is the winter road condition. In this regard, setup 1 was used to conduct the measurements of different winter road conditions: dry, icy, wet and snowy asphalts. Here the illumination source was connected to power through a variable voltage transformer. So by changing the voltage, we were able to change the spectral distribution of the radiance from the illumination source using this variable transformer here. So we can say that when we change the voltage, we basically can change the illumination source. So we took different measurements for the winter road conditions using different illumination source through changing the voltages, namely 3 at we said 50, 100 and 220 volts. And we use the calibration method using the low cost reference to measure the relative reflectance of these winter road conditions. The second test case application was the food waste with polymers. So the idea was to be able to detect the polymer pieces of plastic, like plastic shopping bags, in the food waste. So for this, we worked with the gasification plant in a nearby city, where the truck comes from the city collecting the garbage, the food waste, dump it there. So we took the samples from the dump and took the measurements of the food waste samples with polymers. The third application that we use is the polymer samples, in which we use 6 kind of recyclable polymers, generally known by their recycling codes 1 to 6 or by their abbreviations. We can find these abbreviation and codes in like a lot of them in our fridge, in ketchup bottles and like food packaging. And this test case application we use from paper 2 to 5. From here we move to the discussion part, where we will take a brief look at the results. So regarding the changes in lighting at imaging site, this can be an environmental factor like changing in the ambient light. This also can be a system based factor like changes in the illumination spectra by changing for various reasons it can happen. So as I mentioned before that we took the measurements of the winter road conditions, the snow, ice, wet and dry asphalt using different illumination sources by changing the voltage. And we were able to measure the relative reflectance after performing the calibration using the low cost calibration reference. And we compared these spectra with the known spectral signatures from the other studies. So we were able to accurately measure the spectra of winter road conditions independent of the illumination and the irregular sensitivity of the camera. After that we performed the PCA, the principal component analysis for both the calibrated spectra and for the uncalibrated spectra. For calibrated spectra we can see the well-formed clusters, and for the uncalibrated spectra we can see that the PCA plot is all mixed up, the clusters are intermixing, and from here we can expect what kind of classification result we can get for these two set of data. So as expected, without calibration the error was 25% at its minimum, and with calibration the error was 0 even when only the two principal components were added to the algorithm. Now the changes in the relative humidity at imaging site, this is an environmental factor, and here in this first graph we can see the spectra of a test material, a different spectra that are taken at the different level of humidity, the relative humidity, and the calibration was kept at 20%. So it's like the calibration of the system was performed at 20% of relative humidity. Then just imagine that the humidity is increasing and the system is taking more measurements. So we can see that some misalignment of these spectra, and this misalignment is more at certain wavelength bands compared to the others. And the second graph shows the scenario where the calibration was updated at increasing level of relative humidity, and this misalignment disappears, and here all the spectra are perfectly aligned. The third graph shows the coefficient of variation for the first two graphs. So in the case when the calibration was not updated, the coefficient of variation was reaching up to 6%, and using the frequent calibrations we were able to reduce it to 1 to 1.5%. So from here we find that the change in relative humidity has an impact on the accuracy of the measurement, and using the frequent calibration we can mitigate this effect and can reduce the inaccuracy. However, having the repeated calibration can be challenging in industrial environment and applications, so we proposed here another solution to prune the wavelengths that are susceptible to the changes in relative humidity. So we prune those wavelengths, we take them out from the data, and then we perform the classification of different data set. The first data set where the polymer samples measurement were taken at 83% of relative humidity, and the calibration was at the 23% of relative humidity, and in this case the error was up to 20%. Then we updated the calibration at the same level of the material measurements to 83%, and this way we were able to reduce the error to less than 0.5%. And in case of pruning, despite the big change in the relative humidity, there was a minimal effect on the classification. However, this method for pruning can be application specific. It worked well for our test case application, but if there is an application where a lot of information lies in those wavelength bands, probably this method will not be that effective. The limited dynamic range of the imaging sensors. This is a system-based influence. Here in these two pictures, a same scene is presented, that is the headlight of a car. And the only difference that this image is taken at low exposure and this one is taken at high exposure time. In this picture, you can see the filament very clearly, but here in this picture, but you cannot see any details, more details in this image, and the image with the high exposure time provides you more details in the surrounding areas. Even you can read this sticker here that is completely black here, but the problem with this image is this region is completely saturated and you cannot get any details here. This is an old problem in digital photography, and generally it is resolved by the multi-exposure fusion algorithms. However, the same problem for the kind of camera we use, the hyperspectral line camera, this problem looks like this. This image represents this scene of the sample, this plastic sample. And here we see that this high reflective, shiny, transparent plastic is saturating these pixels here or close to saturation. On the other hand, the area of image that represents this black plastic here is completely dark, maybe touching the noise floor. We cannot be sure, but it's very possible. So deal with such problem for the kind of camera that we use. We first calculated the dynamic range of the camera. So this graph here shows the dynamic range of the camera against the exposure time. However, we set a constraint here of 20 decibel that for any signal to be considered reliable, it should be at least 20 dB higher than the noise floor. So we computed it, and if we add this constraint, so we can see that the effective dynamic range of the system is basically the camera dynamic range minus this constraint. So if we see this constraint here, so the effective dynamic range for this camera will be around 43 dB. In the same way, we calculated the dynamic range of a random food waste sample. These two pictures are representing the same scene of a food waste, and here we tracked two pixels, the darkest pixel in the brightest image and the brightest pixel at the darkest image. We tracked them against the exposure time, and we see that the brightest pixel hit the saturation very early and the darkest pixel remain very close to the noise floor, the dark current, at the maximum exposure time. And using this data, we calculated the dynamic range of the scene, and that turned out to be 56 dB, considerably greater than the effective dynamic range of the camera. So basically, this camera is incapable to image such a scene, that is an ordinary scene, with adequately, means with all that, without losing any detail, it cannot do that. To deal with this problem, we proposed a multi-exposure algorithm that dictates to take several images of the same scene, and the algorithm looks for each pixel in this stack of images to look for the unsaturated brightest pixel in this stack. So if it does not find the unsaturated pixel, it goes down to the next image that is taken at comparatively lower exposure time, and it continues until either it finds that pixel or it hits the last image in the stack. So using this algorithm, we were able to increase the dynamic range of the system from 43 to 73 dB, including the constraint of 20 dB. We also investigated the effect of this dynamic range issue on the classification, and for that we worked with two different test case applications: the food waste with polymers and the polymer samples, the different kind of polymers. And we find that the HDR data set results in 98% accuracy, where the non-HDR is 92, a little higher than the 92% of accuracy. And in the case of polymer samples, the results were even more convincing. The HDR dataset resulted in around 95% of accuracy, where the non-HDR stayed at 35% only. The limited wavelength range of hyperspectral camera, a system-based influence. In this regard, there can be applications that needs the scanning in the broader region of the spectrum, and sometimes the cameras are incapable due to the limited wavelengths they offer, or they are capable of for scanning. One such application is the classification of the colored polymers. In the beginning, I referred to it as a difficult problem or a tricky problem. We will see why. To give the color to the polymers, certain additives are added to the polymers, and the addition of these additives to the polymers cause the changes in sometimes the spectra to the level that a polymer of one type, the spectra, starts to look like the spectra of the polymer of other type compared to the same type. So we took images of several different colors with these polymer samples, the 6 types, and we found 2 cases that were problematic. The half of these images, means this side represents the short wave and this is the visible share. So in the short wave, we can see this red LDP, the red spectra, looks very similar to the yellow PP spectra in short wave, compared to, if you see the resemblance of with the other LDPs of from this red, they too more look alike compared to the other LDPs. And in the same way, the LDP transparent, this one looks like the PP golden spectra in the short wave region compared to the other LDPs here. So we investigated that how it can affect the classification of these colored polymers. So we trained 2 different classifiers, the SVM, one with only the short wave wavelengths, and the other one with the visible and the short wave wavelengths. The first classifier exhibited 25% error rate when only the short waves were included, and the second classifier achieved 2% error rate only for the same LDPs for these 2 troubled cases. The evaluation of convolutional neural network for black polymer classification. So as I mentioned earlier, that there is a general consensus among the relevant researchers that using shortwave infrared, it is impossible to classify the black polymers. However, a recent study claimed 98% accuracy if one-dimensional CNN are used using the shortwave infrared imaging. So using this interesting means it convinced us to work on this problem, and we were actually able to get 98% of accuracy using CNN, not just CNN but also using the KNN classifier. But we noticed that this high level of accuracy is only achievable if the sample set is like very simplistic. So in this case, when we took all the data vectors from the single object, like this one, where this object has the similar physical properties like surface finish and the shine and maybe the densities or the additives. So we were able to get 98%, but when we added the more variety to the samples with the multi pieces, that is still very simple sample, but a little variety. We added 4 pieces, so the accuracy was dropped to 93 in the case of CNN and 69% at the case of KNN. So there is a reason to believe that if the sample is more diverse, probably this will decrease further. So we do not agree with this statement that with one-dimensional CNN only we can use 98% of accuracy. However, comparing these numbers and the results of CNN compared to the other algorithms, we cannot refute the idea that it has potential, and there should be more investigation with more realistic sample or more better samples. From here we move to the conclusions. The research question 1 was, what are the major environmental factors that can reduce the performance of in situ hyperspectral imaging system? So we find that the change in the lighting at the imaging site and the changes in the relative humidity can have the impact on the accuracy of the measurements, and also they impact the classification of materials. The research question 2 was, what are the major limitations of system components that can reduce the performance of in situ hyperspectral imaging systems? In this regard, we find that the hyperspectral measurements can vary with the changes in the active illumination at the imaging site. And we find that in the cases where the dynamic range of the camera is lower than the dynamic range of the scene, in this case the hyperspectral camera cannot measure the material spectra adequately, and it can impact the classification of materials. For particular applications, one camera cannot measure the spectra in all required spectral band due to the limited spectral bandwidth of the camera detector, as we see in the case of the colored polymers. The spectral profiles from low reflective material display very low signal to noise ratio caused by the low sensitivity of the camera that we see in the case of the black polymers. Research question 3, how can we improve methods for image acquisition, processing and system calibration such that limitations and impacts found in research question 1 and research question 2 are mitigated? In this regard, we see in the case of the winter road conditions, the material spectra we were able to measure with precision independently of the spectral distribution of the illumination source and the irregular camera sensitivity using the PTFE based low cost calibration reference. We also see that the use of multi-exposure method was shown to improve the accuracy, to improve the dynamic range of the imaging system and also the classification of materials. We see that frequent calibration or the pruning of the selected wavelength bands can improve the classification of materials. Addition of the visible wavelengths with shortwave infrared by utilizing an additional camera improved the success rate for the classification of colored materials that we see in the case of the colored polymers. Research question 4, can the use of deep learning artificial intelligence improve material classification by hyperspectral imaging system? In this regard, we see that the CNN outperformed other machine learning algorithm in classifying black polymers. However, we also noticed that the accuracy of the system drops as the variety in the samples are increased. In this regard, we recommend more investigation. I think it is required to find the definite answer to this particular research question. What have we learned from studying various applications for hyperspectral imaging? A calibration reference with ideal reflectance of 100% is probably not needed if the purpose of the imaging is to identify the materials using their spectral signatures. The small changes in the imaging setup can affect the measurements considerably. The shortwave infrared hyperspectral imaging is very reliable. We find it in identifying winter road condition, and the technology can be used with confidence in the relevant application. With the advancement in machine learning and optical sensing technologies, effectiveness of existing hyperspectral imaging can be increased with the aim to resolve the bottleneck problems in material classification like the black polymers. As an overall, this thesis presents methodologies for improved robustness against the impacts from the changes in relative humidity, changes in spectral distribution of lighting at the imaging side, low dynamic range and the low camera sensitivity, the limited spectral range of the photodetectors. As a future work, we would recommend to test the proposed methods with real-world samples. Most of the samples and the test applications that were used in this work were either in the lab environment or the sample size were limited. So to have a better picture on the effectiveness of the proposed methods, it would be good to test them with the real-world samples. More powerful illumination source that also offers the possibility of modulation with respect to the changes in the ambient light, so it can compensate for it. The fine tuning of machine learning algorithms. A lot of classifiers and the classification was done in this work, but little effort was made on the fine tuning of the machine learning algorithms, because mostly the idea was to compare this the classification with or without the proposed method. So in this regard, there is much room for improvement, I think. The generation of 2D images followed by image segmentation into group of pixels. In the case of scanning, where the setup 2 was used, every single pixel was used as a data vector. In the case of a spectral cube, all the like the pixels in the stack, like a column, they were used as one single data vector. However, a better approach would be to scan the area, generate the 2D images, and perform some segmentation to group all the pixels related to one object together. And instead of using one of them as a single data vector, a mean of them to have a one single vector would be better to have better signal to noise ratio. With this, I thank all of you for listening to me. Thank you very much.
Thank you, Saad, very much for your presentation. And now the idea is that we will very soon hand over to the opponent to lead a discussion with Saad about his work. But before doing so, we are going to have a short break of 10 minutes. And we are now also stopping the broadcasting of this seminar on YouTube. So we are thanking very much for all those people that are viewing us on YouTube. And if you want to continue to participate in the seminar, you can also you can join us using this Zoom link. that should be available. So see you all again in 10 minutes.